Okay, good morning. Today I'm going to start a new topic, which is called a simple linear regression analysis. And as you can see on the rightmost part of this page, I have written a path to machine learning. Now, probably after seeing this word, you are getting very excited that probably I'm going to talk about machine learning over here, but no, it is not. I have written this word just because of the fact that linear regression analysis is actually the one of the most fundamental tools to study machine learning. I will try to tell you the connection between the two, but later on, not before we learn what is linear regression analysis actually is. Now, we have come to know about the correlation coefficient between the two random variables, capital X and capital Y, and we have got to know its formula. But yet I am pretty much sure that the most of the facts of correlation related to correlation are not clear to you. That will not be clear to you until you do the calculation or the problems by yourselves. Okay, otherwise the doubts and puzzles will not come to your mind to be clarified. Okay, so correlation and regression is one of the most important chapters of statistics, and I've often seen that whenever a particular student is told to do some kind of statistics on his data, he always tries to do by correlation analysis. People often think that correlation analysis is that easy, but correlation analysis is very confusing, and you have to be well aware of all the facts that you are using. Now, when in correlation analysis, you already know that we have to deal with a bivariate distribution. One variable of which is called is denoted by capital X, and another variable is denoted by capital Y. Actually, we call the variable capital X as independent variable and capital Y as the dependent variable if it is a matter of uh, a linear equation simply. But if it is a matter of correlation analysis, and we are going to find the the line of regression or regression line, then in statistics, often the independent variable capital X is known as the input variable, and capital Y is called the response variable. So the study, if I want to find out the correlation between your study hours that you have spent to prepare for an examination and your performance in the examination, if I try to find out the correlation, in one case the variable is time, in another case the variable is your mark, will be quantified by your mark. So if I want to correlate these two, then your study hours will be considered as input variable, your marks in the examination will be considered as response variable. And if I want to fit a linear relation, if I want to find a linear relationship between these two, because experience shows us or tells us that if a particular student increases his study hour, his result is definitely going to be improved. But it's not always the case, because if a particular student used used to sit for as many hours as he can with his books open but mind roaming here and there, then that is a different issue. But generally, there we all know that there has to be some sort of correlation between the two items, study hours and the marks. But if it is so, and our general knowledge tells us that if one increases, the other increases, so some sort of linear relationship exists between them. Okay, probably these two variables are linearly connected. So if these variables are linearly connected, then the question is, what is the linear connection and what is the relationship between them? Because in this particular case, in this particular chapter, what is happening is that we do not know the equation which is being satisfied by the two variables. We only know their values, but we want to guess the equations. So this is the reverse of the usual process. Initially, we had equations. When we did problems in schools, we had equations, we drew graph. But here we don't have any equation. We have some values of the variables. Now, after doing some sort of mathematical calculation, we want to find out what sort of relationship exists between them. And if we can find such a relationship, then that, and if that relationship is linear, okay, where the variables are correlated with each other, then such a relationship is called regression relation. And the straight line equation that connects both the variable capital X and capital Y is called line of regression. So I have shown here a line of regression in this case, which is a general form, obviously, where we have the response variable on the left hand side, we have the input variable on the right hand side, and alpha and beta are parameters. They are behaving just like we write y equal to mx plus c, where here we have considered m to be our beta and c to be alpha. But one extra term has been added here, that is called e. That e is actually gives you the random error whose mean value is 0. So several times if you are collecting the data, and if you want to find out if you can find out this type of the values of response variable depending upon the values of the independent variable, and if you consider the difference of y and alpha plus beta x, that will count e. And if you do it several times and then you take the mean of e, that mean will be 0. So random error e will be having mean 0. So it is written that the relationship between response variable y and input variable capital X specified in the preceding equation is called the simple linear regression. Somebody has raised his hand. You want to say something? You can unmute yourself and say.
No, sir, by mistake.
Okay, no problem. Now, the question is, we know that we can find out the linear relationship between the two variables if possible, if they exist at all. But we have to find out that whether the linear relationship between the variables can exist or not. So that can be done by putting the variables, the values of the variables inside the software and plotting them in a curve. And the curve, you actually know, it is called scatter diagram. So often when we set the values of the response variable and input variable in the software, and the software gives us the curve called scatter diagram, by looking at the scatter diagram, we come to know whether they bear any sort of relationship between them or not. Okay, say for example, I'm not going to read out this particular problem. This particular problem, just treat that this is capital X, this particular column is capital X, and that particular column is capital Y. Okay, I am not interested about what is written above. It is some sort of problem where capital X and capital Y are given. But if I now ask you that these are the values of capital X and capital Y, do they have any sort of linear relationship between them? Immediately you cannot answer this question, because these values are not systematic. Now these values are not very large in number. Okay, so a thorough inspection, if you take some time and give a thorough inspection to the values and individually, then probably you can guess that, yeah, maybe there is a kind of relationship between them. But question is this relationship linear? Now, if you want the quick answer, then only one possibility is there. You just draw the graph and try to look at it and try to guess whether a linear regression line can be fit on that or not. So what I have done using the Excel software is that I try to fit this particular values of the variable capital Y with respect to the values of the variable capital X, and this type of curve actually emerged. Now, any sane person can say that this curve is actually not linear. Okay, and by some tools, I have drawn the straight line also, tried to draw the straight line also, that I'm going to show you in today's class how to do this. So I try to draw a straight line like this, but you see that if I forcefully try to draw a straight line, if I forcefully say that, yeah, there are some kind of linear relationship between them, it is observed that Out of all these points, only one point is falling on the straight line. All the other points are actually scattered around straight line. These points are above the straight line, these points are below the straight line. If you drop perpendicular from these points to the straight line, okay, this perpendicular will give you the difference of the actual value that y should take and the observed value that y is taking, and the difference of these two values or the length of this perpendicular that will be dropped from the point to the straight line actually counts E, gives you the value of E, which is error. But any sane person can say that this, with respect to the given problem, you cannot fit a linear regression line. So we shall skip this particular problem. We'll try not to fit any regression line forcefully. Then I have considered a second problem where I have taken very simple values for capital X and capital Y. Now I want to see, I want to look at this particular problem and want to draw the scatter diagram to check whether we can fit a linear regression to this particular set of values or not. Okay, so while doing so, I saw that this points are actually moving in this particular direction. Although the number of points are pretty low, only 4 points are there, but okay, I can guess their movement. As the capital X is taking the values in increasing direction, capital Y is also taking the value in the increasing direction. Okay, so now this as these values are actually in increasing direction, and if you try to put some sort of straight line passing through these points, then you will probably find out that most of the straight line will pass out through these points. Most of the straight lines will pass out through these points, and you can fit a better straight line with respect to the given example. Now, which I am going to, first of all, with respect to the given problem, I'm going to show you how to fit a straight line using the software. So let me note down the values of capital X and capital Y in my copy, because when I will stop sharing this file, then this file will not be visible to you. So we have the values of capital X as 1, 2, 3, 5, and capital values of capital Y as 4, 7, 8, 12. First of all, I'm going to talk about how to fit a straight line using Microsoft Excel to a given set of data. Okay, so I'm stopping the share. I have actually tried to fit several straight lines. You can see in my Excel sheet, so many problems are actually already have been done. So let me show you another problem. It's kind of practical demonstration. So I'm going to put the values of X like this, and I'm going to put the values of Y like this. So that these 4 values have been plotted. Now we will select the data. We'll go to the insert section, and from insert section, we'll choose the scatter plot. Take the first one, and you see the curve which I got. I was showing you that curve has been obtained over here. Okay, so this is our curve. Now, as you can see that here there is a key of this form. Okay, it is different sort of layouts of the scatter diagram are available. So this is one layout. So if I click on it, it is showing you the straight line. Directly it is showing you the straight line. But we do not know, a straight line has been observed, but can I say that what sort of relationship exists between capital Y and capital X? Okay, why this straight line is in this increasing direction? Is the correlation between capital X and capital Y is perfect correlation? Immediately you can say that the correlation between capital X and capital Y is not perfect, because one particular point is not falling on the straight line. it is above the straight line. So it cannot be a perfect correlation, but we can say that it is they are positively correlated and the correlation between them is pretty high. It would be much better if I do the correlation part calculation also. So I'm actually taking a blank cell, going to the formula section. In the formula section, I am choosing more function. From there, I'm choosing statistical, under which I'm going to select correl. Correl stands for correlation. And the first row is selected like this in array 1. The second row is selected like this in array 2. And as you can see, the correlation has come out to be 0.989476. As I told you that the correlation between them is pretty high, which can be easily guessed by looking at the form of the points and their movement, their mutual movement in the plot. But what is the equation that is being satisfied by these two straight lines? What is the form of that equation? Y equal to alpha plus beta x. Okay. So for this, if you want to find this equation using the straight line, using this set of values, what you need to do is that you take your cursor, click on the straight line like this, and I will take my cursor on a particular point, and I will click the right button of the mouse. This particular window will come out. From this window, I'm going to select the section which is called Format Trend Line. I will click on it. Then this particular window will emerge. This window gives me the trend line options and some other forms of the curves. Exponential curve, logarithmic curve, we can fit a polynomial curve also, and so on. What do we need right now? Right now, we have the set of values. We have capital X as our input variable, capital Y as our response variable, and we want to find out the linear relationship between them, because we know the linear relationship exists between them. So I want this software to display that particular equation for us. Okay, so what we will do is that we will click on this button, which is called display equation on chart. We will close it, and you see this equation will come out. Can you see? This is the equation that will come out. It is showing us that the relationship between y and x is 1.914x plus 2.4. Y equals to 1.914x plus 2.485. Okay, so that is the thing, that the relation has already been obtained. Let me save the data. Okay, so by software, in this manner, we can easily find out the regression equation between the two variables. Now I'm going to stop the share of this Excel sheet, and I'm going to go into the whiteboard, and I'm going to talk about how to find this particular equation by manual calculation. This equation that we have found is of the form alpha plus beta x. Now the E part is not there. I'm not coming to the E part. E part, you keep it aside. I will talk about E part later on. But first of all, I'm going to talk about how to arrive at this particular equation. Okay, so for this, I need to do some kind of board work. And whatever I'm going to talk about right now, you just listen to me very properly and attentively, because it is very important. Usually we know that this is a prerequisite that I'm going to discuss, but that prerequisite has not been discussed earlier. So it's very important. Just pay attention. Usually we know that covariance of xy between two variables is given by the formula 1 by n summation xi minus x bar into yi minus y bar. This is the usual formula of the that is given by the this is the formula for covariance between x and y, and this formula has a computational form also, which can easily be derived, which is 1 by n summation xi yi minus x bar y bar. In my earlier notes, probably you have seen this. And also we know that variance of x is given by the formula 1 by n summation xi minus x bar whole square. Sigma y square is given by 1 by n summation yi minus y bar whole square. And their computational formula is given as follows. The computational formula of sigma x square and sigma y square are 1 by n summation xi square minus x bar square and 1 by n summation xi yi square minus y bar square. We have already known this. Okay, and but what we do not know is, and also we know that standard deviation of x is the positive square root of the variance. Standard deviation of y is the positive square root of the variance of y. But what we do not know is the following. Now, listen to me very carefully. There is a chapter called estimation theory in statistics. Estimation theory. In estimation theory, this chapter is not there included in your syllabus, but in this theory, what we learn is that we try to find out a particular sample measurement which will best estimate the population measurement. Now, in estimation theory, all the population measurements are actually called population measurements are actually termed as parameters, and sample measurements are termed as statistic. So with respect to this, you can say that population mean, population variance, population mean deviation, population median, population mode, any measurement that you can assume related to population, they are called parameters. But you know that parameters cannot be calculated. Parameters can only be hypotheticated. These are hypotheses. We can assume the values of the parameters. But who is going to estimate your parameter? Who is going to test your parameter? That test is actually done by the sample. And any corresponding sample measurements like sample mean, sample variance, sample mean deviation, sample median, sample mode, they are known as statistics. So in estimation theory, what we learn is that what is the best statistic that will estimate the parameter, its corresponding parameter. And during the analysis, it has been found that if we consider the sample covariance of this form, if we calculate the covariance with this formula, okay, as it is given, it doesn't best estimate the population covariance. If we calculate the variance with this formula, sample variance with this formula, it doesn't estimate the population variance in the best possible way. So what needs to be done is that a simple correction needs to be done. There is a huge analysis about that. A proof is that, a theorem is there, but since estimation theory is not there in your syllabus, so I'm not going to discuss the theory in details, but it has been observed that if instead of dividing this particular item, that is summation xi minus x bar into yi minus y bar by n, instead of doing this, if I divide this by n minus 1, and while calculating the variance, if I do the similar thing, if I divide the quantity by n minus 1 and not n, then it has been observed that In these circumstances, the covariance, sample covariance best estimates the population covariance. Sample variance best estimates the population variance. So this is the best measurement. The only difference is that instead of dividing this by n, we are dividing this by n minus 1. But also you have to carefully observe that if we do so, this particular computational formula or this particular computational formula will not come out of covariance xy and sigma x square and sigma y square. Let me demonstrate that particular thing. So what I'm telling you about that covariance xy, if you do it by the formula like this, if you divide this by xi minus x bar into yi minus y bar, their summation is being divided by n minus 1. And if I want to simplify this expression, let us try to see what comes out of it. So we will get summation xi yi minus x bar summation yi minus y bar summation xi plus x bar y bar. And if you further simplify it, then let us keep summation xi yi as it is. Now you know that summation yi by n, summation yi by n is equal to y bar. So summation yi can be written as n into y bar. Similarly, summation xi by n is your x bar. So we can write it as n into x bar into y bar plus there was a summation, I missed it. Just a minute. Not only x bar, y bar will be there, a summation part will also be there, summation over 1. So that how many terms are there? Small n terms are there, and therefore that would be equal to n into x bar, y bar. Now one x bar, y bar and one x bar, y bar will cancel each other, and ultimately we'll get 1 by n minus 1 summation xi yi. This is equal to n by n minus 1 x bar y bar. Now look at this particular formula and that particular formula. Just look at it. They are different. These two formula, that the computational formula that has been obtained, they are different. So if I am going to use these best sample measurements, this cannot be the computational formula. If I want to use the best measurement, sample measurement like this, the computational formula will not be that. So you have to keep this in mind. Okay. Now, once we do so, let us try to see what happens to the correlation coefficients formula with these best measurements. So correlation in this case, Rxy in this case becomes, as you know that Rxy is defined as covariance xy by standard deviation of x into standard deviation of y. So in this particular case, if I write 1 by n minus 1 summation xi minus x bar into yi minus y bar, and if I write it as 1 by root over n summation xi minus x bar whole square 1 by root over n minus 1 root over summation yi minus y bar whole square, then you will see that this term will cancel each other, and only thing remaining would be equal to summation xi minus x bar into yi minus y bar divided by summation xi minus x bar whole square under square root sign summation yi minus y bar whole square under square root sign. And you see that this particular formula of correlation is independent of the sample size. So sample size actually doesn't affect the correlation coefficient. Okay, so by seeing this, now if we have these values, different values of x and y, as we have the values 1, 2, 3, 4, 4, 7, 8, 12. Okay, then to calculate correlation coefficient between them, we need to calculate this in the following manner. We'll write it as xi and yi. Then we'll calculate from this column, we'll calculate x bar. From this column, we'll calculate y bar. And then we shall introduce the column xi minus x bar. We will introduce the column yi minus y bar. And then we will introduce another column which is given by xi minus x bar squared, yi minus y bar squared, and lastly we will count xi minus x bar into yi minus y bar. All the summations calculated from this chart will be put over here and the result will come out. We already know by our statistical software this correlation coefficient's value is 0.98. I will ask you to check this result manually by doing manual calculations. So we already know that this is the correlation coefficient. Now our objective was to find what is the form of this equation actually, and that can be actually done if we know that what are the values of alpha and beta. Okay, now for the time being, if we ignore this error part and we just concentrate on the relation y equal to alpha plus beta x, since alpha and beta are not known, they can be estimated. And let us consider that the estimator of alpha is small a and estimator of beta is small b. Then the y estimate will be a plus bx, or you can write it as estimator alpha plus estimator of beta into capital X. But what is the formula? First of all, let me talk about the formula directly. In the next session, I am going to elaborate this formula in details. Okay. So the formula which can be derived, and that will be shown in the next session, is the following. The regression equation that we are going to find out are of the following forms. Regression equation of y on x. There are actually two regression equations. One is called regression equation of y on x. Another is called regression equation of x on y. The first equation is given by the formula y minus y bar is equal to r. R means the correlation coefficient. Here I am considering r to be the correlation coefficient between x, y. Sigma y by sigma x into x minus x bar. And second regression equation that can be obtained is x minus x bar is equal to r into sigma x by sigma y into y minus y bar. Remember, these two regression equations are actually very different from one another. So what you can do is now you can calculate, you have already calculated the values of y bars and x bars from here. You can substitute those values in this place. We have the value of correlation coefficient. Okay, so you can substitute those values. You substitute the value of y bar from the chart, calculate sigma y from the chart, calculate sigma x from the chart, substitute the value of x bar. And if you substitute all these things together in this equation, probably this equation will come out, will emerge. You can check it by doing the calculation. this equation will come out from the given regression equation of y on x. Also, you can take the help of the software in this regard. Okay, I'm stopping the share and I'm going to the Excel chart, and let us try to find out the different values that I'm interested about using the Excel. Okay, it will just save our time. First of all, suppose I'm interested in finding the average. So in this case, I will select a column. Okay, and in this column, the column heading I'm writing as average of x. And under this column heading, I'm going to calculate the average of this variable capital X. So I'm selecting more function. From there, I'm going to select average, and that will be for capital X. And you see that this average is coming out to be 2.75. Similarly, if I want to calculate average of Y, we select this particular blank cell, go to the more function section, again click on average, and now I'm going to select this row, this column, B2 to B5, and the average will come out as 7.75. If you want to calculate standard deviation of X and standard deviation of Y, then also you can do it. So you go to the statistical section, try to find out the relevant key, which is this is standard deviation. Okay, so if I select it and I select from capital X to capital, I select all these values, all these 4 values, the standard deviation will be calculated as this 1.707. And similarly, if I select the second one and do the similar calculation for the column Y, the standard deviation will come out as 3.30. So you can do it by Excel software or any statistical software that you can get hold of, but I will suggest not to do so. You always try to do it manually. Okay, manual calculation is very important before you delve into the domain of softwares. Now you have all these values. You have X bar, you have Y bar, you have sigma X, you have sigma Y, you have the correlation coefficient. You have the correlation coefficient between the two variables. Okay, now all this you have calculated. Now what you need to do is that you have to substitute all these values. I'm going to write these values in my copy. You are going to substitute all these values in the formula of regression line and check whether this equation is coming or not. Now we have less than 1 minute for this session. We are again going to continue in the next session. Okay, so I'm stopping the recording at this point.